So just going over solutions, again, we talked about these a little bit a while ago, but here we can have gaseous solutions, liquid solutions, and solid solutions. And the solvent in a solid solution will be a solid, and you can have a solid dissolved in a solid. These are metal alloys are solid solutions. You can also have gases dissolved in solids and liquids as well. Liquid solutions are things we more commonly encounter in chemistry labs. The solvent phase is liquid, and you can have gases, liquids, or solids dissolved. Gas solutions, anytime you have two or more gases together, they make a solution, because gases always mix homogeneously. That's not always the case with liquids and solids. When we refer to solubility, we mean the amount of substance that will dissolve in a given amount of solute. So solubility is actually a more quantitative term. We can actually put a number on that and say, about 50 grams of this will dissolve in 100 grams of solvent, or something like that. So let's go back to that tendency towards mixing. Many physical systems are going to tend toward lower potential energy. And we talked a little bit about that, about how reactions are going to proceed if they are energetically favorable, if it causes a lowering of energy. The bond will form if it results in a lower energy. It's like rocks rolling down a hill, going to lower potential energy. Now, forming a solution doesn't necessarily lower the potential energy of the constituent particles. So there's something else going on here. If we think about mixing neon and argon gases, here they're separated in a container. If we remove the divider, they will spontaneously mix. Does the fact that they are now mixed lower their potential energy? No, it doesn't really affect their potential energy at all. So there must be something else going on that's causing the gases to mix. And that something is called entropy. Entropy is similar to enthalpy in how it sounds and how it's spelled. They're both measures of energy, but entropy is a measure of the energy of randomization or energy dispersal in a system. When you have those gases mixing, the kinetic energy of each gas becomes spread out when it mixes. And so the entropy has increased. Entropy always wants to increase. Entropy is a measure of disorder. Think a deck of playing cards. Okay, and you've got them all lined up by suit and by number, ace to king, and then you play 52 card pickup, right? You flick them. What happens to them? They disperse, right? That's entropy. It's things spreading out, things becoming more disorganized. My home is sadly a living testament to the power of entropy. Oh my goodness, it's just mind-boggling. And I have my little entropy agents who go about and assist entropy. So substances mixing, they mix due to this pervasive tendency for energy to spread out whenever it is not restrained from doing so. So the reason that things mix together is because then the energy is dispersed, the energy gets spread out, and that is, entropy has increased, and that is a favored process. This also explains why thermal energy flows from hot objects to cold ones. Because when the heat spreads from the hot thing to the cold thing, it has spread out, and energy spread increases entropy. Intermolecular forces have a great deal to do with the formation of solutions. So we just finished talking about these, but let's just review them real quickly. We have the dispersion forces. These are present in all substances, but they're the only force in nonpolar substances and in atoms. Then next up in strength is dipole-dipole forces. These are forces of attraction between polar molecules. Hydrogen bonds are just like super duper dipole-dipole forces. They're just much stronger. You have to have hydrogen bonded to oxygen, nitrogen, or fluorine. And then we have ion dipole forces. And those are between an ion and a polar molecule. And these are the strongest ones. So these intermolecular forces can promote the formation of a solution, or they can oppose it. So we've got different interactions going on when a solution forms. We've got interactions between the solvent and the solute particles. We've got solvent-solvent interactions and solute-solute interactions. If all of these interactions are similar, then a solution will most likely form. And the way we remember this is the little phrase, like dissolves like. If we've got a polar solvent and a polar solute, the chances are good that it will form a solution. But if the solute-solvent interactions are much weaker than either the solvent-solvent or the solute-solute interactions, then entropy doesn't make up for the energy loss. Because in order for the solution to form, the solvent molecules need to spread out and allow the solute in. That means that those interactions need to be broken. And in order for the solute to dissolve, the solute-solute interactions have to be broken. If the solvent-solute interactions are very strong, they can make up for that. And it will form a solution. If these are very weak, they're not going to compensate for that. And if the entropy gain doesn't make up for the energy loss, then the solution will not form. And you'll have your solid sitting as a lump on the bottom of your beaker, or you'll have your oil floating on the top of the liquid. So again, we're talking about like dissolves like. So determine whether each of these compounds will be soluble in hexane. What do we know about hexane? It's got 6 carbons and some hydrogens, right? Because we just took a little teeny tiny step into organic chemistry. So is hexane polar or nonpolar? Nonpolar. Decidedly nonpolar. So let's just make a note of that. This is nonpolar hexane. So then we're going to look at each of these. Is water polar? Yes. Oh yeah. So polar and nonpolar, are those going to dissolve? No. Soluble? No. How about ammonia in hexane? This is also polar. Okay, because nitrogen has a lone pair, and so it makes that trigonopyramidal shape, and it's a polar molecule. So that will not be soluble. How about propane? This is a nonpolar. Will nonpolar and nonpolar mix up? Yes, they will. So that'll form a solution. How about hydrogen chloride? Polar. Hydrogen chloride is a diatomic molecule, just hydrogen and chlorine. They have different electronegativities. It's polar. It's not going to mix. Any questions?